Hi grade 12s, and welcome back to my channel once again. It's been a while since we've had a session, and I hope you have gotten enough rest, and I hope you are deep in the preparation of our trial examination. But most importantly, guys, I also hope that the June exam has gone very well, and we all know from here on we have 2 more terms to go. We have trial and final, and these are preparations for trial and final. And as you can see, today we are going to have a look at electrodynamics. It is a new topic in grade 12, as you have not touched on it in grade 11. So some terms might be new, but all I'm gonna say is bear with me, guys. Be open-minded and be receptive, because in this chapter it's not a very long chapter, but what is important is for you to know application of what we're doing here. Okay, so with electrodynamics we are dealing with how electricity moves. So as the word says itself, electrodynamics. So we are going to focus on the movement of electricity, the movement of charge. Remember, guys, when we say electricity, we actually mean charge. How is charge moving? How is current moving? So the movement of electricity, I'm just gonna put in a bracket that this has to do with charge or current. Okay, let me be specific. Let me say current. So this is electrodynamics, and when we now want to view how this current is going to move, we have 2 devices of interest that we will focus on. We're going to have a look at what we call a generator. Most of you, I know you are quite familiar with the generator, and we also are going to have a look at a motor. So these are the 2 devices that we will use to illustrate how electricity moves. So in grade 11, okay, just to shift a little bit on what we did in grade 11 under magnetism, if you go back, you would remember that in grade 11 we did the stuff where we had a look at Faraday's law, where we had a look at what happens when you take a conductor and you put it between magnets, meaning you put it in a magnetic field. We know that it's going to induce, the magnetic field is going to induce an EMF. So under this chapter we are also going to make use of what we did in grade 11 to say for a generator and a motor, we are going to make use of magnetic field and see what happens when you rotate a conductor in a magnetic field, or what happens when you put a conductor in a magnetic field and provide power to that conductor, or have a power source. The conductor is going to move. So with our generator and a motor, just to highlight the differences, which yes, you do need to know because you will be examined on that, a generator and a motor. So the key differences between these 2 devices, the first one is that with a generator, what happens is we have the energy conversion, which is from mechanical energy. So we are converting mechanical energy to electrical energy. So remember, mechanical energy is movement. So mechanical energy to electrical energy. So what we are doing is we want to start with movement and generate electricity. So I just need to put that in electrical energy. So what we mean here is with a generator, you provide motion to a device, and from that movement you're going to generate electricity. And with the motor, it's the other way around. We are converting electrical energy to what? To mechanical energy. So this is the energy conversion for each device. You need to know it. They do always they do test us on that one. And then the next thing is that with a generator, we are going to make use of what we call the right hand rule. Okay, yes, I know you might be questioning yourself, what is the right hand rule? I'm going to demonstrate or to illustrate that to you. Yes, we are going to make use of our hands. So this one, guys, even during an exam, yes, there will be a point where people will be busy with their hands, and it would be meaning that they are on electrodynamics. You are going to make use of your hands to answer some of the questions. And then for the motto, we use the left hand rule, which I'm going to illustrate as we move. And then the last thing on your motor and your generator, I just want to highlight the type of devices, a type of a generator and a type of a motor, meaning a type of a device where you start by mechanical energy converting it to an electrical energy. The generator, the most common would be like the generator that we use at home. So I'm just gonna write generator, because we know, guys, with generator we use it as backup at home. So when we don't have electricity or during load shedding, some people do have generators, and what happens is the generator, if you think about how, if you have seen how they switch it on, so there is a it's not really a wire, but there's something that they pull out multiple times, so you keep on pulling it until the generator starts to make a sound, until there's something that is rotating within the generator, and as that rotates within the generator, electricity gets produced. It means the mechanical energy as that device inside. I'm not quite sure with the names of the devices inside of a generator, but what we know is the moment they start to pull that pulley, let's call it a pulley, or whatever name we can give it, and then the moment the generator starts to make that sound, then there's something that rotates very, very fast inside of the generator, and as it rotates, that's mechanical energy, and what it does is it converts to electrical energy, and we are able to use the generator. And with a motor, an example of a motor would be a car battery. So with the car battery also, because in a motor we say we are converting from electrical to mechanical. Inside of the battery there's electricity, and that electricity will now be converted to mechanical. Mechanical is when the car starts to move. So those would be the differences between your generator and a motor. Okay, so now let us look at just a structure of a generator and a motor, just to show how mechanical would be converted to electrical energy and how electrical energy would be converted to mechanical energy in both structures. So starting with a generator. So with the generator, I'm just gonna try and draw, I'll try and be as creative as I can, just to draw what we call an armature. So this is just it's not like a fully detailed representation of your generator, but just to show you how it will look, and also how the energy conversion will come about. So because we said we are going to have this, coil in a magnetic field, it means the magnetic field would be as a result of the two magnets. And then because we say from mechanical to electrical, we need the coil. This one there represents the coil. This is the coil that we are going to rotate. Let's say it has a handle there. Well, this is not something that you should really know. Let's say that is the handle, and then we take the coil or the conductor, we rotate it. So as we rotate it, and this rotation is taking place where? It's taking place in the magnetic field. What will happen is EMF is going to be induced, and then EMF being induced, that would be observed now in the load or on the external circuit. So you would see that we have a voltmeter connected, meaning as we rotate through the handle, as we rotate the handle and the coil starts to rotate, we are going to see a reading there to show that EMF has been induced. So that is the whole idea behind a generator. So this would be the coil, then this would be the voltmeter. It's not always the voltmeter. We can put any other devices. We can put a light bulb. We can connect a light bulb, and we know if electricity gets generated, the light bulb will be bright. If we now have a look at that of a motor, so with a motor, because energy conversion is the other way around, yes, we still need the two magnets. So you would have seen also that I drew two magnets, and we know a magnet will each have a north and a south pole. Same there on a motor, we need two magnets, north and south, and then another magnet there that has north and south. And then we have the coil in between the magnets, meaning on the magnetic field. And then we have remember guys, I have said this is just to show you how energy conversion takes place. This is not how a typical structure of generator and motor would look in an exam. I'm still gonna bring structures of the type of the examples that you would come across when you write exam. So for this one, because we need to start with electrical energy and move to mechanical, we need a circuit. So you'd see here I have a circuit that has a cell, and the moment let's say we also have a switch there. The moment the switch is closed, current is going to flow, and as current starts to flow and it moves into the conductor being in a magnetic field, the conductor will now do what? It is going to rotate. So it means you would see now that we are moving from electrical to mechanical energy. I hope you are still following. I hope you are still with me. This is the whole idea of how a generator and a motor works. Meaning, if it's sitting in between the magnets, it is experiencing magnetic field. We know magnetic field lines would be there, and then they will always be from north to south. Same there, it is experiencing the magnetic field, which is from north to south. Okay, so now that we have seen, we have looked at how a generator works, and we also had a look at how a motor works. I'm going to show you how you're going to use the right hand to tell the direction of rotation on a generator, whether it's clockwise or anti-clockwise, and also how you're going to tell the direction of current using the left hand rule. So starting with the generator, firstly you have your hand and you have your fingers at 90 degrees to each other. Your thumb represents the rotation. Is it clockwise or anti-clockwise? Your index finger represents the direction of magnetic field. It's always, it never changes, it's always from north to south. And that, the last finger, represents the direction of current. And then before we can even get into like the illustrations, I just want to highlight something. So because we are saying with the thumb, it's going to tell you if whether it's clockwise or anti-clockwise. We know guys, if we say it is clockwise, I'm just going to indicate it on my diagram. It's going to look something like this. It will always, if they say clockwise and they want to show it with an arrow, it means the arrow is pointing to this side. And when we say it is clockwise, that is going to mean that because the arrow is pointing at this side and it's not pointing at that side, the side at which the arrow is pointing at is the side that has to go down. Meaning if I am going to use and also the other side is the side that goes up, which is that one. If I'm using my diagram now and say clockwise, it's going to be, the arrow is going to point there, so that is clockwise. It means when the rotation starts to happen, this is going to rotate like that. You see the side that is pointing, the side at which the arrow is pointing is the side that goes down once the rotation starts, and the other side is the one that goes up. Same with your thumb. If you find your thumb facing up, it means for that side specifically, the side is going up. If you find your thumb facing down, it means the side is going down. Like that. So that's how your thumb is going to tell you if whether the side is going up or down. Okay? That is with this one. And let's say it was anti-clockwise. So it would mean I'm just going to indicate it with the blue pen. So if it's anti-clockwise, it looks like that, then we expect that side to go down because the arrow is here. We expect the other side to go up. And if I'm going to use that, guys, this is my coil. I hope it does look like a coil. And if I use my coil to indicate that it's anti-clockwise and the arrow is pointing there, so I have something like this. The arrow is pointing there. This is the side that goes down and the other side goes up, so the rotation will go like that, meaning my thumb for this part is going to go down, but my thumb for that part is going to go up. Okay, so it means your thumb facing up, it means the side that you are focusing at specifically is the side that goes up. The thumb facing down, it means it's the side that goes down. So that's how we're going to use clockwise and anti-clockwise, the thumb and also the arrows on the diagrams. And now let us have a look at an example. So I'm just going to label my diagram to be A, B, C, and D. And the first question, we want to know the direction of current, no, not current, the direction, rotation. I'm just gonna do that because, guys, we're looking at a generator, so it means we want to tell the direction of current. So let's say we want current on the side AB. Okay, so the side AB is this side. I'm just gonna move, so they will provide with the type of rotation. So if they say we have a clockwise rotation, and having a clockwise rotation, we know, guys, this is already like the arrow that shows the clockwise rotation. What is the direction of current this side? No, let's start with AB. What is the direction of current that side? AB. So we are going to put our fingers at 90 degrees. The first thing that you need to do is always going to be the magnetic field, because you always have it. It's north to south, and you can see my north is to the left, my south is to the right, so my finger is going to face in that direction. Facing. And then now, because we're looking at the side AB and we see it's where the arrow is pointing is the side that's going up, it means my thumb, without changing that finger, my thumb goes down. And then now you can see the current is away from me, or away from whatever we're looking at, away from the screen, not away from me, away from the screen or away from the paper in the case when you're writing an exam. So if it's away, it means, please guys, take note. If it's away, it means the arrows are going to point downward. This means away. Okay? So it means the direction of current is going to be from B to A. B to A. Okay? And if we look at CD, let us look at CD. So we still use the same thing. For CD is the side, this is still north to south, and that is still, because it's the side that goes up, it means my thumb is going to face up. And then you see now my third finger is pointing into the book, into my screen, and if it's pointing into, it means the arrows must point into. This is how the arrows would look. So it means for that side, it's going to be from C to D. It is that simple. We are done. That is how you're going to tell the direction of current provided clockwise. Clockwise, thumb up, the side goes up. Thumb down, the side goes down. Into the page, the arrows point into the page. Out of the page, the arrows point down, like out of the page. Now let us look at a motor. Okay? So now with the motor, remember we had said we're going to use the left hand rule. Still fingers at 90 degrees. You have your thumb still telling rotation. We have that still telling magnetic field, and that telling what do we call the current. So one thing about a motor is that, remember guys, with a motor we had said we are converting from electrical to mechanical. So that means in motor you have the direction of current. This one you always have it, that one you always have it. You want to know rotation, is it clockwise or anti-clockwise? So now there's something that I want to highlight with regard to a motor. With motor we make use of what we call conventional current. Conventional current states that current flows from positive to negative. So current will flow from the positive terminal to the negative terminal of the battery. And how do you tell if it's positive and if it's negative? Let us say we have a battery that looks like that. The longer ones represents positive, the shorter ones represents negative, positive, negative. And this is connected to, let's say this is connected to a second, something like this. The direction is going to start from this side. So because we are saying from positive to negative, that would mean that we are going positive, 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 all the way to negative. So it's always from positive to negative. That's how you're going to tell the direction of current. So let us look at an example. I'm still going to label A, B, C, D. But in this case now, guys, remember you have, because it's a motor, we need a battery because we need to start from current. You need to start with electricity and convert it to mechanical, where we want to see the coil rotating. So what we want to find out here is the coil going to rotate clockwise or anti-clockwise? So let us start with let us start with current, because already we know we have north to south. We have our fingers at 90 degrees. Let us say, okay, now we are starting with the side CD. I need to get a black pen. We are starting with the side CD, and we want to tell the direction of rotation, or the type of rotation for that side. Or we want to tell the type of rotation for the entire thingy, for the entire coil. So it means, in order for you to tell, let us look at current. Our positive terminal is there, our negative terminal is there. It's not there, it's there. So it means current is going to flow in that direction. It means it's going to go up there. It means on side AB, current is into the page, and then on side CD, the current is out of the page. So it means, in order for you to tell if whether you have clockwise or anti-clockwise, you need to figure out, is AB going up or down, or is it CD going up or down? So let us start with CD. So we have our fingers. I still have north to south. I need to figure out that one because it's the rotation. And then now current there is down, like the red arrows represents current is downward, meaning is out of the page, meaning it's gonna face me, and then you'll see that side faces up. It means this side CD is facing up. And then if it faces up, automatically the other side has to face down. Always. If you find one side, you're sorted with the other side. Meaning, or we can also prove if it's going to face down. So if you look at the side AB, we have that north to south, but current is into the page. So current into the page, my thumb faces down. So it means current there is facing down. If I draw the arrow, we know the side that's going to go down is the side where the arrow has to point at. So it means it's going to look like that, and then as a result, it means this side is going down and that is going up, so that's going to be clockwise. Okay, I hope it makes sense, guys. I hope it makes so much sense. It is that simple. Just make sure you use the right hand. Generator, right hand, right. Okay, just make sure you use the correct hand. Generator, use the right hand, and then motor, use the left hand. Okay, so now that we have looked at our generators and motors, we have looked at the differences between those two. You know, you can tell it's a generator if when you look at the external part, you have a load or you have a light bulb, anything that will tell you that, or you have a voltmeter, anything that will tell you that now electricity has been generated. And then with a motor, you will see it by having an external circuit that has a battery, because you need to convert from electrical to mechanical. So now we are going to look at DC and AC. So DC is direct current, and then AC is alternating current. So with these two, they just tell us how current is going to flow. Meaning whatever I'm going to say about DC, you know, all the properties of DC will apply for both a generator and a motor. All the properties of AC will apply for both a generator and a motor. So I'm just gonna start by just listing the differences between the two, between DC and our AC, and you do need to know them because we do get tested on them. With our DC or our direct current, what you should know is that with direct current, in this one, current will flow in one direction. So current flows in one direction. Meanwhile, with AC, current flows so it doesn't flow in one direction, it can go backward and forward. So it flows backward and forward and forward, or forward and backward. So that is the first difference between DC and AC. And then another difference, which is what you will now be able to see whenever you're looking at a DC structure, is that a DC has what we call a single slip ring. No, a single split ring. It has a single split ring commutator. We also call it commutator. So a commutator is a split ring, meaning it looks like this. If I am to draw how the ring looks like, it's something like this. So it is split in the middle. So it's supposed to be a ring, but it's a ring that is split. So it will look something like that. There's this gap there in between. That is your split ring. And then with our AC, it has two slip rings. So in most cases AC, you'll have something like this, two rings that are not split, they are not cut. So this would be an AC. Okay, I can do better. So that would be the two slip rings. So it means, yeah, that's how you're going to tell if whether you're looking at a DC or an AC, by just looking at the structure of either a generator, because you can have a DC generator, you can have an AC generator, you can have you can have a DC generator, you can have an AC generator, you can have a DC motor and AC motor. In order for you to tell that you're looking at a DC, you will see a split ring. In order for you to see that you're looking at what do we call an AC, you will see slit rings. So that is these are the differences between your AC and your DC. Then if we look at structural, so here we have a DC motor. A DC motor. I will tell you right now why I'm saying it's a DC motor. So firstly, it's a DC motor because if you look at this part there, this is the ring, and you would see the ring here is split. So I'm just gonna label that. So I'm saying it's a DC because it has split ring. And then I'm saying it is a motor because we said a motor, you'll see it by an external circuit that has a battery or a cell. So hence I'm saying it's a DC motor. Then we can also label, here we have the magnets. We know the magnets are there to create magnetic field. And then we have the coil, which has been labeled for us. We also have the brushes. I'm just gonna also label that. I didn't highlight on that. We have what we call the carbon brushes. And the main function of the carbon brushes is that they link the coil to the external, or the circuit. Yeah, they link the coil to the external circuit, or yeah, so they link that part to that part. So those would be the function of your carbon brushes. And then there we have the external circuit, and then we have said that this would be the negative, this would be the positive part of the battery. And then if we have to look at this one will definitely be an AC. So we can't really tell if it's a motor or it's a generator because we don't have this part there, but it's an AC structure. Why? Because it has these two rings. So it has two slip, I hope I said split there. It has two slip rings. I hope you're still with me, guys. So that is how you're going to differentiate. Is it an AC or a DC? If it has two rings that are not split, then it is your AC. If it has a single ring that is split, then it is a DC. Okay, so those would be our AC and DC, how you can differentiate it from the diagrams during an exam or during a test. The next thing that I want us to have a look at is graphs. So still under DC and AC, I'm going to start with DC. We have graphs that we can use. We have a graph that we can use to represent your DC current. So you can either be an EMF graph, or it can be a current graph, or it can be magnetic flux. But yeah, in all, the graphs will be the same. So now with our DC and AC current, or our DC and AC, we have graphs that represents each. So I'm just going to draw a graph of DC and AC just for you to see the difference, or to be able to identify the two. So I had mentioned earlier that for the graphs, you can either have an EMF graph, EMF and time, current and time, and also your magnetic flux and time. But all in all, I had said also that the graphs, they all look the same. So for direct current, because we had said it moves in the same direction, the graph would look like that, and this graph represents one cycle. So on the y-axis we have EMF, on the x-axis we have the time in seconds. And then for your alternating current graph, because this one, it moves in opposite direction, it goes backward, forward and backward, the graphs would look like that, the graph would look like that, and we still have EMF being represented there and the time being represented there. Just a few things that you need to know from the graphs, because we have EMF and the time. What you have here is what we call Vmax. So that part there is the Vmax, making that part there to be V minimum. Same there, what you have there at the peak of the graph is your Vmax, and what you have there at the minimum part of this part there, you have your V minimum. So these are the two things that you need to be able to label from your graph. And then because I'm saying the graph represents one full cycle, so the reason I'm mentioning that is because every time when you have to draw a graph, you need to know how to show that it's one full cycle. So it starts there and it ends there again. That is one full cycle. Or you can say, for a graph to be a full cycle, you need to have the minimum, maximum, minimum, maximum, minimum. Not in that order specifically, but all in all, you must have 5 points. You see my red points there? It's 5 of them. You must have 5 points to represent a full cycle, which is also the same on your alternating current graph. So with the AC graph, we have minimum, maximum, minimum, the 0 point and the minimum and the 0 point. But all in all, the main reason I'm bringing this is for you to know, in order for you to test if you have a full cycle, you must have 5 dots. If there are 5, then it's a full cycle. Another thing, because what you can see from the graph is that I keep on saying minimum, maximum, or I'm saying 0 or peak, 0 or peak. So you need to also know what happens with the rotation. Remember, this is showing the rotation of what? The rotation of, I don't know if the rotation of this coil. It shows the rotation of this coil. The rotation can either be vertical or horizontal. When it's horizontal, I meant it's when it is lying flat on the surface, when it is vertical, or when it is perpendicular. So when it's horizontal, we can also say it's parallel. When it's vertical or perpendicular, when the coil has raised up, so it's standing upright, it's perpendicular to the surface. So you need to know that when the coil is lying flat, or when the coil is parallel, that's where you have these maximum points. At the maximum, you have where the coil is parallel, and then at the minimum points, there, and there, you have where the points are perpendicular. Meaning when it's perpendicular, it's when it is 0, not minimum but 0. Okay, that's what you should know, which is the same with this graph. It's 0, it's when it's gonna be perpendicular, and then at maximum or minimum, it's when it is parallel. Okay, I hope you are still with me. So the reason I'm bringing maximum, parallel, minimum, or 0 perpendicular is because whenever you are being asked to draw a graph, either a DC or an AC graph, you need to know if whether you're starting from 0 or maximum, depending on what? Depending on whether it is perpendicular or it is parallel. So I'm just going to show a simple example on how you can tell. Let's say for this one, you have an armature, and we have to draw. Okay, let me use that one. We have to draw this one. It has a split ring, which would mean that it is a DC motor. Okay, it's a DC. Let me just say DC, and then we have to draw a graph out of this, provided that it is starting at a parallel position. So starting at what? Starting at parallel position. At parallel. Already we know at parallel it's when it is at maximum. So I'm not going to go in details onto the number on the time that it takes. I'm just going to show you how it's going to look. So it is a DC, and if it's starting at a parallel position, it means it starts where it is at a maximum. So it means you have to start at this point. You're not starting at 0, because 0 is when it is what? It is perpendicular. You start there, the graph will go and sit there. The graph will go something like that, and then it will end at the same position again. How do you tell that it has to end there? You count the number of points. You have 1 point, 2 point, 3 point, 4 point, 5th point. 5 points. This is one full cycle. We still have EMF, and we still have time. EMF and the time. I hope you're still with me. So that is how to know whether you have to start at maximum or 0. Had they said the graph, the coil is starting perpendicular to the starting condition is when the starting position, it's when it is perpendicular. It means perpendicular, we know it's when you have 0. So it means if it's let's say now, okay, this was for a DC. Let's say now you have an AC. If it's an AC and it has to start at what? At perpendicular, it would be like that. But if it's an AC that has to start parallel, it would be something like this. Because AC, remember, it has to go to the negative and to the negative, to the positive. All in all, you still have 5 points there, and you still have 5 points there. 3, 4, 5. Okay, I hope it makes sense. So that is what I wanted to highlight on minimum, maximum, or parallel perpendicular. So now that we've drawn our DC and our AC graphs, which I'm going to draw again there, I'm just going to underline that, which is not a very nice line, but I tried. So for DC, we had said, because the graph or the current is moving in one direction, it's starting at 0, you have maximum, 0, then another maximum, then it's a full complete cycle. You have EMF, and you have Vmax over there, and then you have V minimum. So from this graph we can calculate the V average, the average EMF, V average, or the average velocity. It's going to be Vmax plus V min divided by 2, but because our V minimum is 0, it means it's just Vmax divided by 2. That is how we can find average velocity from a DC graph, a direct current graph. Then can we find the average velocity from our AC graph? Let us check that. So I have I'm just gonna squeeze them. I'm gonna try and squeeze them there. So we have AC over there, and we know the shape already, and we have EMF, we have Vmax, we have V minimum. V minimum should actually be like the graphs should be the same, so V minimum and V maximum must be the same in magnitude. Then if we want to find V average, we have seen V average is Vmax plus V min divided by 2, but Vmax and V min are the same. It's just that V min is going to be negative, so that would be Vmax minus V min divided by 2, and because they are the same magnitude, it's going to be 0 over 2, and that is going to be 0. So we can't really find average velocity, which is also the same with current. If you think about current, let's say now let's say now we make use of current, and I have Imax. Remember I had said the current graph and the magnetic flux graph are the same, or the voltage graph are the same. Same thing, if I want to find I average, it's still going to give me 0, because it's going to be Imax minus I mean divided by 2, which is 0 over 2, so that's 2. So now, since we cannot really find the average velocity or the average current, we can now bring a new parameter, because we are looking at V and I, and we have a formula of power that brings a V and I together. Power equals to current times velocity, meaning you'll keep on multiplying the current, the velocity, and the current. And if you have a look at it, when I multiply the velocity there, it's going to be multiplied with the current there at the same position, meaning if I multiply the velocity on this one section, I'm going to multiply it with the current, not the velocity, sorry, the voltage. How did we get to VPM? So if I multiply the voltage Vmax, or voltage, with the current, it's gonna be everything in that section multiplied by everything in that section. And because they're both positive, I'm gonna end up with power that is positive. So because it's positive, it's just gonna be on the positive x-axis. If I look at now this section, I'm gonna multiply every voltage there with the current there. I'm still gonna consider the sign, so that's negative times negative, so it's still negative times negative is positive, so it means we are able to generate a power graph. It's P there, and it's time, and we still have the same thing, we still have P average. Okay, so it means if I am to do P average, P average is going to be I average times voltage average. Meaning I can still get the very same thing there. I can still get what? I can still get P max, and this is gonna be P minimum. And from that we can still find P average. You see, now I can find, for alternating, I can just change it to a power, and then power gives me a graph that will enable me to calculate P average. It's gonna be P max divided by 2, because that's just P max minus 0, since P min is 0. P max plus 0 I meant. But with P max, I can replace P max with I max times V max divided by 2. And now I'm going to bring in a new term, which we call root mean square. With root mean square, what I'm going to do is, I know that I'm still keeping my I max and my V max. I can replace 2 with square root of 2 times square root of 2. Please plug square root of 2 times square root of 2 on your calculator. That should give you 2. So it means I have replaced 2 with square root of 2 times square root of 2, because I want to now have I max over square root of 2 times V max over square root of 2, and this whole thing now we call root mean square. So it's gonna be I RMS times V RMS equals to what? Equals to P average. Okay, so guys, you don't really have to know this whole derivative that I've written over here, because when you do the calculations under this chapter, you do have like all of these equations, all of these formulas on your formula sheet. But what I just wanted to show you is how we have moved from those two alternating current graphs to the power graph, and how we use the power graph to now derive the formula to calculate the average power. Okay, so that is the formula that we're going to use to calculate average power. And you can always, if you want to calculate current root mean square, it is equivalent to current max I max over square root of 2. Voltage root mean square it is equivalent to Vmax over root mean squared over square root of 2. Okay, so the next thing that we can do is we can do changes to these graphs. We can manipulate them, because what we are doing here, this is the graph of when for example, if we are looking at a DC generator, when when the coil gets rotated, and the coil being rotated, it induces EMF. I'm going to take us to grade 11 when we did Faraday's law, which was EMF equals to, okay, let me write that as EMF. Yeah, that is EMF equals to the number of rotation times the change in the magnetic flux divided by the change in time. From this, and according to Faraday's law, we know that EMF is directly proportional to the number of rotations, which is N, meaning the faster the rotation, the more EMF you have. So the number of rotations according to Faraday's law and according to that formula. And EMF is inversely proportional to the time, meaning now if we extend the time that it takes to generate the EMF is going to be small, you know. So if we can think about it in terms of doubling, halving. So let us say let us look at time now as a vector that gets changed. So what happens to the EMF if we double, to the EMF and also to the graph, if we double the time? Meaning we are doing it now. If we double the time, it means we know doubling the time means you take a long time to complete one cycle. So it would mean that you are going to generate less EMF, and it means the number of rotation decreases. So it means if you double the time, what happens is you have the EMF. So if we are to draw, the graph of, how do I put it, the graph of DC, of an AC. Let's do the graph of an AC to say, okay, if the original graph of an AC looks like that, and we have Vmax there as 50, and we have Imax there as negative, V mean there as negative 50. This is for when it's the normal graph. But now when you, and that the time is 0, let's say the time is 0.5. It takes half a second to complete that full cycle. But now if you double the time, it means you are now taking if you double the time, it means you're now taking more time to complete that full cycle. So it means if the time was 0.5, you now double it to what? You double it to 1 second. And if you say if you double the time, EMF is going to be halved. It means the EMF is going to be there at 25, at negative 25. And since you still complete a full cycle in that, the graph is going to look something like this. So our EMF, our Vmax is 25. Okay, I know it looks very skewy, and our V minimum is negative 25. Okay, this is one of the changes that can happen. What happens if you halve the time? So now we have the time. According to that, if you halve the time, it means the time decreases, you take less time. I'm still going to reference with that one. So if I halve the time, it means the EMF is going to double and the number of times will double. So my EMF was 50 on that first graph. So now it means I'm going to, if I halve the time, it means I'm going to take half of 0.5 to complete a full cycle. 0.5 divided by 2 is 0.25, and that is 0.5. So we say, what do we do when we have the time? We double the thingy, so it becomes 100 there, Vmax becomes 100, and that becomes negative 100. And we say we take half of the time to complete a full cycle, so it means we expect something like this. So it means you're going to complete 2 cycles now in 0.5, because when you have the time, it means you take less time to complete the cycle. So it means the speed becomes faster. You take less time to complete a full cycle. So that the graph would look something like this. You now have tens. 1 2 3 4 1 1 full circle, 2 3 4 and 2 full circles. So whenever they bring these factors where they half and they double, please write down that equation on your side and see the relationship. If you double the time, since it's inversely proportional to EMF, the EMF is gonna half. If you triple the time, the EMF would be 1/3. Just it always affects the EMF in that relationship. And then if you now change the number of rotations, if you increase the number of rotations, it means you also, if you double rotation, you're also doubling the EMF, but you are halving the time. So that will be how you will always interpret the relationship. Okay guys, now let us have a look at yet another example. We have the diagram below is this is a past paper from September 2023. It's a trial exam paper. The diagram below is a simplified representation of a generator. The coil is rotated clockwise. So we have two keywords, a generator and the coil being rotated clockwise, and we also have an arrow that is indicating the clockwise. Is the above a DC or an AC generator? Remember, we had said the observable thing that you can use to tell if we're looking at a DC or an AC are the rings. And if you check the rings, we have 2 slip rings. It's 2 of them. Remember, AC generator, we said you have 2 slip rings. So this is going to be an AC generator. Then write down the name of component X. Component X over there. Or okay, we've already mentioned that these are slip rings. And then write down the function of component Y. So component Y are these connected to the carbon brushes. So the function of them is to bring electrical conductivity. So they connect the rings to the circuit. Electrical conductivity, conductivity between the slip rings and the external circuit. Okay, and then question 9.1.4 is the direction of the induced current from P to Q or Q to P. So our side of interest is this side there, PQ or QP. They want to know the direction of current. So I'm just going to explain it. Okay, it's fine guys, you can pause the video and determine the direction. Remember, you are using the right hand rule because we had said it's a generator, so we have to use the right hand rule. So I hope you did pause the video and try the question. And now I'm just going to explain how now you're supposed to face to position your fingers. So remember, you have your right hand rule and you make sure that your fingers are at right angle. And then because we know with the index finger is the one that we always start with, our magnetic field is always from north to south. So meaning you're moving from north to south, so that has to be your index finger pointing to the right. I hope you have the right hand. Make sure you have the right hand. Index finger pointing to the right. Yes, it's gonna cause a little bit of a strain on your hand because that's our hand cannot rotate very well in that direction. So your index finger is pointing to the right, and then the next thing is your thumb, because remember the thumb has to do with the rotation. We have a clockwise rotation, and we know clockwise rotations means the side where the arrow is pointing at is the side that has to go down, and the side where the arrow is pointing is pointing away from is the side that has to go up. And remember, if that side goes up, it means your thumb must go up. Oh, I hope that's the correct spelling for thumb. I'm not sure if I'm supposed to put a P or a B there, but guys, no, this is not an English lesson. You'll correct me in the comment section if my spelling for thumb is not correct. But your thumb finger must be up. So the side that goes up means the thumb must go up. So now you have your index finger pointing to the right because we are saying it's north to south, and then your thumb must point up. Thumb must point up. So if your thumb is pointing up and your index finger is to the right, on your right hand side or on your right hand, your third finger must be pointing towards the screen. I hope you got that. Your third finger is pointing towards the screen, and that would mean if it points toward the screen, meaning it means if you put the arrows there, they must face the screen. So it means the direction is P to Q. That would be the correct direction. I hope we are still together. Question 9.2, the graph below shows the output voltage from a household AC generator for the rotation of a coil for one complete cycle. So we have the output voltage, and we can see we have the V max there, we have the V minimum there, and we have the time that it takes to complete one full cycle is 0.02. Okay, so looking at 9.2.1, the question says the speed of rotation is doubled. Interesting. Sketch the graph of the induced EMF versus time for this change for one cycle. Indicate the maximum voltage and relevant time values. So they are being specific. They say of this change for one cycle. So it means on our new graph, we're only drawing a graph for one cycle. Remember guys, I had said with these changes or these manipulations, we are going to use Faraday's formula. EMF equals to the number of rotations times the magnetic flux divided by the time. So we said the time is inversely proportional to EMF. Let me just write that also. Time is inversely proportional to EMF, and EMF is directly proportional to the number of rotations. So what we are doing here is we are taking the rotations, we are doubling them. If you double the rotation, because it's directly proportional to EMF, it means you also double. So I'm just going to indicate that with a blue pen. You double the rotation, you also double the EMF, but now EMF is inversely proportional to the time, so you're going to half the time. So it means the two EMFs there are going to be doubled and the time there is going to be halved. So I'm just going to draw a new graph to the side of this one to show now how the new graph is going to look. So we have doubled the rotation, and we had said the time is going to be half. So it means the time now 0.02 divided by 2 is 0.01, and then 3.11 times 2 is 311,13 I mean, times 2, that gives me 622,26, meaning there also have negative 622,26. Don't forget to label, that is the time in seconds, then that is the output voltage. Label that output voltage in V, in volts. And then now it means the graph is going to be something like that. So the EMF has doubled, the time has halved. I hope it helps. Please always make use of that to find the new graph. Okay, 9.2.2, an electrical device is connected to this generator. So we are now on this generator there on the first statement. The maximum current passing through the device is 8 amperes. So we have Imax is 8 amperes. First question, calculate the resistance of the device. So the formula for resistance would be we know, resistance would be V is I times R. So R is V max over I max. Remember, always your V max must always go with I max. You can't use V max and I RMS. If they are all maximum, they must be all maximum. So V max was 3.11, right? We keep on saying 3.11. 311,13 divided by maximum current was 8, and 311,13 divided by 8, that gives me 38,89 ohms. So that is my R. And then B, calculate the energy the device consumes in 2 hours. So now they want energy. Remember, energy, guys, is work. So, and we also have time. So we know a formula that combines these two. We know P average would be equals to work over time, but we don't have P average. We have multiple formulas that we can use for P average. I'm just going to scroll down for us to pick up the one that can be best suitable for our calculation. We have P average is VRMS times IRMS. P average is I squared times R. Okay, we can use that one. You can use any as long as you have all the parameters or all the values for the parameters. So now finding P average, I just need to separate that. So P, okay, I'm going to use a blue pen so that it doesn't. P average, we had said it's IRMS squared times R. And then remember, IRMS, guys, according to the formula sheet, where is that? Okay, I need to scroll down further. IRMS is Imax divided by 2, and we do have Imax. So IRMS, not IRMS, IRMS is Imax, which is 2 divided by square root of 2, and then our V is our R is 38,89. So I need to square that. I must not forget to square that. 38,89. Hope that is visible because I'm squeezing them now in a very small space. 8 over root of 2 squared times 38,89. That gives me the P average of 1244,48 watts. Then we are looking for work, so work would be P average times the time, and time, remember, it must always be in seconds, so that is 1244,48 times 2 hours times 60 seconds times 60 seconds, because we need to move from hours to minutes, and from minutes times 60 minutes times 60 seconds. So that gives me 2 times 60 times 60. That gives me a value that is 88,960,256 joules, because we are looking for energy. Okay, I hope it makes sense. I hope, guys, from this you can score all the marks for this chapter, because yes, the questions will always be around these principles over here. Thank you so much, guys, for watching my videos. I'm very grateful for the people who have subscribed into my YouTube channel, and please stay tuned for more. We are in the 3rd term, so we know the next thing that I'll be doing for our next video would be straight into electrochemistry. And please stay tuned, stay subscribed, so that you can get notified when I upload the next video. Thank you so much. Bye, guys.